We're going to be solving a problem here related to intermolecular forces. So the question here is, what type of intermolecular forces do we have in these molecules? And then how that impacts the boiling point. So I'm going to write down, these are the molar masses, so very similar. And as you can see, all of these molecules, these have 5 carbon, but here I am replacing one of the carbon by an oxygen. Here is the same 4 carbon and an oxygen. Here 4 carbon and an oxygen. So similar, but functional group wise is different. That's a cycloalkane. That is an ether, cyclic ether. That is an aldehyde, and this is an alcohol. Now the boiling point of these is 49 Celsius, 66 Celsius, 75 Celsius, and now butanol is 119 degrees Celsius. So let's explain this. So the impact of the intermolecular forces on these, say, bulk properties, so which is the boiling point. So now, all of these molecules, we're going to say what is London dispersion forces. So these are, remember, the fleeting, very weak interaction, fleeting dipoles on that. And that occurs whenever you have this between, say, a chain like that and another chain like that. They will feel, this is butane, some interaction, but this is very weak, although it adds up when you have molecules that are larger. So these fleeting dipoles is what we call the London dispersion forces or van der Waals. And it will be present in all of the molecules. So I'm going to give it a check mark here. Then let's see the other interaction that we're interested in. Do we have dipole interactions? And here, this is permanent. This was fleeting, interaction because the electrons are moving in the bonds. This is, however, a permanent dipole. And so now we need to be considering for this the difference in electronegativities here. So now oxygen is more electronegative than carbon, so you will have a dipole, a vector going in this direction. So this is a plus, delta plus, and this is delta negative, and of course you will have another vector. These two you add up and you will have a net dipole. So these molecules have some dipole. So of course it has, this has 0 dipole because in this molecule we have only carbon and hydrogen, so we will have 0 dipole moment. However, here we have, considering that type of interaction, dipole, in this is 1, 2, 3, 4. So this is butanal, an aldehyde. There will be an H here. I'm going to draw it so we don't forget it. In this, I forgot to say, this is cyclopentane. And this is THF. We call it an ether. This is tetrahydrofuran. Furan, I'm going to write it over here. Furan is this. So if you add the 4 H's, becomes tetrahydrofuran. Is that. So butanol, and this is butanol. So an alcohol. Now, there is a permanent dipole here in butanol. Here you have the oxygen is more electronegative than carbon, so you will have that arrow pointing. This is delta positive, this is delta negative, but that's permanent. And a stronger, say, dipole than here. And also, we can visualize this also using resonance structures. I'm going to draw that over here to show the importance of that dipole. If I do this, I can draw a resonance structure in which I'm going to have the oxygen with a formal negative charge, and here a formal positive charge of the carbon. So that contribution of that, we can see that on the arrow of the dipole, but here you have the contribution of that resonance structure. So I expect that that dipole contribution is larger for that. And of course, the bond here in butanol, you will have also this. being delta positive at the carbon, delta negative at the oxygen. And now I'm going to show the hydrogen separately, because here also, of course, you will have another dipole like that. And it will be similar to the when we draw, let's draw water here. If I draw water, I will have that arrow, one like that, one like that, and these two add up, and you will have a permanent dipole. That will be water. So similar to that, we have those two vectors adding up. So that interaction is there. So London dispersion force, again, is everywhere. But that's the weakest. In dipole-dipole, we have in these three molecules: THF, butanal, and butanol. Last type of interaction that we're going to be analyzing is hydrogen bonding. And we need to remember that hydrogen bonds occur when you have a hydrogen attached to an electronegative atom, such as oxygen. It can also be with nitrogen, and of course with the most electronegative atom, which is fluorine. But in organic molecules, this is what you will be seeing. So now let's do the analysis of that interaction. So we need to be looking for that. I don't have hydrogens attached to oxygen or nitrogen. I don't have a nitrogen or an oxygen. In THF, you have an oxygen, but you don't have H's attached to, all of the hydrogens here are attached to carbon, so we don't have hydrogen bonding. So not in cyclopentane, not in the tetrahydrofuran. And now here, with molecules of the same kind, here, pay attention that this molecule, this hydrogen, is not attached to an oxygen. It's attached to this carbon, an sp2 carbon. So this is not this type of hydrogen. So these molecules will not form hydrogen bonds with molecules of the same type. So we need to pay attention that that hydrogen needs to be attached to either of these elements. Now let me erase this for now. And lastly, what do we have here in water? Well, we do have a hydrogen attached to hydrogen. So we will have hydrogen bonding. In that interaction, we can do, say, R, OH, and I will have this with another molecule of the same type. And I could have this network in the bulk of the liquid. So all of that forming. So having said that, the hydrogen bonding we know is the strongest of this interaction. So from the strongest to weakest, this is the strongest, then this is not as strong, and that's the weakest. So we see here that in cyclopentane, I only have the London dispersion forces. So the interaction between molecules is much weaker than it is here. And when it is weaker, we need less energy to have the, let's say, we need to break intermolecular forces between molecules to go from the liquid phase to the gas phase. And I need less energy to do that, less kinetic energy. So boiling occurs at a lower temperature. Here, we have another interaction that is stronger, which was not present in the previous molecule. So what is happening here is that now molecules are, say, attracted to each other by a stronger force, so I need a bit more kinetic energy. So the boiling point temperature is higher, even higher here with this due to, we already analyzed this dipole in that structure, and also the contribution of resonance, so that interaction will be stronger. Therefore, I need that higher temperature, more kinetic energy, so the molecules to break from the liquid to the gas phase. Lastly, here butanol, you have the three types of interaction, being this is stronger, and you require more energy to break those apart so that the molecules separate into the gas phase.